Exercise 7. Develop a math model for the problem. Describe the type of math problem that has resulted. Using assistance from the TI Nspire CAS, solve the math problem and interpret the solution. Additionally, if appropriate, Calculus 3 students should provide a calculus solution and examine it for consistency with the TI Nspire assisted graphic solution. The United States Post Office has rules for regular commercial parcels. One of these is as follows. Except for parcel post and parcel select, no mail piece may measure more than 108 inches in length and girth combined. Length is the measurement of the longest dimension, and girth is the distance around the thickest part, perpendicular to the length. What are the dimensions and volume of the maximum volume rectangular package that can be sent as regular commercial parcel? Record or round all final dimensions to the nearest inch and the volume to the nearest cubic inch. Okay, let's get started by defining some variables here, and a picture would probably be a good way to help do that. So we have this arbitrary parcel here. Perhaps we could call this x, this y, and the length we'll call z. Okay, so we're going to let x, y, z be the dimensions illustrated. And we have decided to have the length to be z. Okay, and the main quantity in this question is volume, so I suppose we go ahead and we let V equal the volume. For a rectangular package like this, we can formulate that right now. That would be the x times the y times the z. Okay, and this question wants us to maximize this. Now, subject to, okay, the domain, the allowable x, y, z's. What have we got there? Well, first of all, there's the idea of physical sense. Okay, if you're the measurement of the length of a side of a package, you gotta be positive. So this has us claiming x greater than 0, y greater than 0, and z greater than 0. Okay, I guess we could call those inequality set 1 there. And what else? Well, we did say the length was to be z. So z has to be at least as long as x or y. It can be equal, but it has to be greater than or equal to. Okay, so length is z. This will give us z. It's got to be greater than or equal to x, and z has got to be greater than or equal to y. You could call that collection of inequalities 2 there. Let's see, what else have we got to control what is allowable for x, y, and z? Well, there's this big statement here that one of the rules says the length and girth combined cannot be more than 108 inches. Okay, so length plus girth no more than 108 inches. Okay, so let's translate that. Length is z, girth around the package, around a cross section perpendicular to the length. So here, how far around is that? You got 2 x's and 2 y's to traverse in that distance there. So look like this comes out to be claiming that z plus 2x plus 2y less than or equal to 108. That could be inequality 3. Now, if you look at the kind of problem we've got going on, volume here is a function of 1, 2, 3 variables. You realize if we were to try to look at the graph of this, we would need 4 dimensions. It's not going to work. This is a potentially troublesome problem. However, consider this. We do seek the maximum volume. Now, this restriction here, length plus girth no more than 108 inches. Well, for any candidate of maximum volume, this has got to be equal to 108, because you can't leave some of your length here unused, because obviously you could, if this is say 107, you add these together and they were 107, well, of course you can increase the length by 1 more inch, and of course you increase the volume, so it doesn't make sense to have considerations where this is anything but equal to 108. Okay, so let's make a note of that. Okay, so important here. Note that for any candidate package for maximum volume, we must have z plus 2x plus 2y equal to 108. Okay, we can call that 3a. Well, now that we have this could become a source of substitution for z, and then that would cut us down to just having a function of 2 variables here for volume. We could furthermore substitute into all of our domain inequalities and create really a whole new problem. Okay, so by substitution of this 3a, a new problem is created. It looks like this. Okay, now we're going to have maximize v equal to, okay, we got here x times y, there comes z, so now we substitute this idea, which, by the way, would be a matter of saying z equals to 108 minus 2x minus 2y. Okay, so here's 2 versions of 3a. And then here, 108 minus 2x minus 2y. Okay, and then we have subject to, let's see, our inequalities set here. Okay, x greater than 0 stays the same, y greater than 0 as before. A chance to substitute z in here. Z greater than 0 now becomes, after this substitution, 108 minus 2x minus 2y greater than 0. Or maybe writing this in a more straightforward way, we could perhaps add 2x and 2y to the other side there, and moving over here, 2x plus 2y less than 108. Okay, this could be a collection of inequalities 4. And going further, z was the length. Now these 2 inequalities also generate another system here. We have, there's z, so again they have the 108 minus 2x minus 2y greater than or equal to x. Okay, let's see, we could add 2x and 2y to both sides, allowing us to rewrite this as 3x plus 2y less than or equal to 108. Okay, this could be 5. Similarly, this inequality with z greater than or equal to y now then becomes 108 minus 2x minus 2y greater than or equal to y. We could add 2y and 2x to both sides and have this look like 2x plus 3y less than or equal to 108. That could be number 6. Okay, looks like we have about everything that goes with this problem. Now here's our math model. Maximize this v equaling this expression here, subject to, okay, the domain is constrained by all these inequalities. What kind of math problem is this? This, okay, optimization, maximize this function. We got x, y, then multiplied by an expression that has x and y in it. So this is nonlinear, a nonlinear optimization question, and these inequalities that describe the domain, each is linear, but doesn't matter. Once the objective function here is nonlinear, this pushes this whole question into the realm of nonlinear optimization. So, okay, we were supposed to answer that as part of this question here. So, this math model is a nonlinear optimization problem. Okay. Well, looks like we might do well to start this by maybe let's get a graph of this domain to help organize ourselves, and then we will take a look at the function itself using the Nspire calculator. It's going to require a 3D graph. Okay, first this domain, and this domain, I suppose we could let's plan on using the calculator for the domain as well. Okay, since we're going to do that, let's get prepared for that. Okay, we have x greater than or equal to 0, rather x greater than 0, y greater than 0. This is the quadrant 1, basically, telling us that. This here, okay, using the calculator. Well, we could divide both sides by 2 first of all, by the way. X plus y less than 54, and solve for y, y less than 54 minus x. Okay, this will be the version we go to in our calculator usage. This here, we could solve for the y pretty easily here. Subtract 3x from both sides, divide both sides by 2. We're looking at y less than or equal to, parenthesis, 108 minus 3x, divide by 2. Okay, that's number 5. Number 6, anticipating calculator usage. Let's get y solved for here. Subtract 2x from both sides, divide both sides by 3. Y less than or equal to, parenthesis, 108 minus 2x, divide by 3. Okay, got our 5 inequalities here. We're ready to go calculator. Okay, here at the Nspire, we start up our new document, and let's add a graph. Okay, as far as this system of linear inequalities goes, I'm looking at these boundary lines, and though we don't really have to do this, it's not too hard to kind of spot the kind of coordinate system that'll make this fit. First of all, x greater than 0, y greater than 0, that's quadrant 1. Then looking at these inequalities as far as x and y intercepts, it looks like I'm seeing numbers like 54, 36 running throughout this. Okay, let's set up a coordinate system that fits those kind of numbers immediately. And so I'll go to the menu and set up a window. And let's give ourselves a little bit of room to either side of these intercepts. So for instance, instead of 0, maybe I'll just a little bit of negative 5 for x max. And let's see, anticipating needing 54, maybe go to 60. Scale every 5 units perhaps. Y-axis, same idea. How about a -5 up to 60? Scale every 5. Okay, we are ready to start here. Alright, let's see. Now again, the first pair of inequalities just put us in quadrant 1. Let's go to number 3 and put that in the entry line here. Need to delete that equal sign, and it is y less than 54 minus x. Okay, so we need the less than there, and 54 minus x. Alright, there we go there. Let's go and return to this entry line. Going to inequality number 5. This will be y less than or equal to, okay, that's number 1 there. We have in parentheses 108 minus 3x divided by 2. Okay. Oh, you notice that sort of relegates the first inequality as being entirely redundant, as its shaded region is all entirely within that of the first inequality. Okay, we keep going to number 6 here. It's y less than or equal to the quantity 108 minus 2x divided by 3. Okay, entry line, delete that equal sign, less than or equal to. In the parentheses, we got 108 minus 2x divided by 3. Okay. Well, we can certainly see what the domain of this function is going to be. It's in the first quadrant and all within this dark blue here. Okay, so let's get this precisely graphed up and in one, say, nice red color, for instance. Okay, well, we're going to need this intersection point here, so let's maybe start there. We can call on this graph here and analyze and go for an intersection. The second graph could be this is this green one here, a lower bound, well, right about there. Hit enter. Start moving over to the upper bound and look for the intersection to appear. Hit enter at this point. Okay, now we have that. That's about it for an intersection. The other points on this domain, let's see, let's take get the y-intercept of this blue line. We need that. Alright, what to do here? We can start off tracing it and immediately just press it, put in the number 0, forcing x to be 0, and then hit enter, and that creates the intercept calculated there in the lower right, and then enter again to get it planted right at our vertex location. Okay, now let's see, we want to get the x-intercept for that green line. Let's see, for a minute, maybe I'll slide everything up here for a moment. I did not want all this labeling to appear. Okay, let's see. Let's try to get rid of all this labeling. It's kind of just getting in the way for the time being. So how can I do that? One thing is I can go back to the settings, the graph settings. Here's what I probably should have done even in the beginning, because when you have a lot of inequalities or a lot of graphs, the plots labels are a little too much to put on a small graph. So automatically hide these things for now, say OK to that, and now let's return to where we were. And now it's okay, now it's much cleaner. I think I'm going to bring this graph back down to about here. Now back to this green line. Let's glide down here and watch the 0 appear automatically for us. Okay, right there. Enter, and that gets it planted with its coordinates right there. Okay, we have our vertices of this domain. The origin is another vertex, but I think we are ready to start to delineate it and color it in. Let's push escape to stop the tracing tool. We have in mind a shape. Polygon 4. Okay, let's start with the origin. Shows up as an intersection point. Good. Got that one. I'm up here to there. Point on. Okay. Over to this intersection. Gotcha. Back down to this 0. Point on. There. And fully connect. Back here. Okay. Now I'll put escape to stop sketching polygons, and let's take the polygon we have and let's go with the coloring of it. First, the line color I'll say would be red, and the shading fill color also a bright red. Okay, looking better. Now I would like to go ahead and get rid of all these other colors, and in fact just keep the boundary line labels that we need. Okay, so for that we could go back to the entry line here, pull up what we've got, and start just turning these back into equalities. So delete that 3 and enter. Okay. Could go up here. The second one. Delete that. 3 for enter. There's that multiplication dot right there. Gotta get rid of that too. So forward and then backspace to delete it. Enter to lock in that there. Back to this third inequality. Want to delete that. Make it an equal to. Delete the multiplication sign there. Enter. Okay, now we're starting to see just our region here, so it's starting to look better. I think at this point it's probably okay. Maybe we go ahead and put in the labels here, and so we can call for a label of 2. That's the green line. Let me bring this label over to where it's close to the green line, right about there. This blue line. Let's get its label and move it to perhaps about there. This red line doesn't seem to play much of a role in anything. I think we'll just delete the thing altogether and have just what we need in sight. Okay, and something else that might be kind of nice, and that's labeling the main object here. This is the domain. Okay. Looks pretty good. Alright, now that we have that, we can go ahead and graph the function v. The volume of this box is a function of x and y. Now, the Nspire won't allow us to have just a domain like this and only graph above this region. We're going to have to do a little bit of work to get that created. But what we can do is we can realize what is it we need to provide for an x and y axis in the 3D graph by looking at what we have here, and we see that x has to go out 0 to 36, and y needs to go from 0 to 36 as well. And then it's true we'll be seeing a little extra graph above whatever is here, because if we make x and y go 0 to 36, that's a rectangular type of bottom there, and so we'll have a little extra graph which we can take care of in Paint if we import our 3D graph in there and then take care of it. Okay, so next mission is now to go to another page and start our 3D graph. So Control, add a page, add a graph, and this time we can go to the menu, View, 3D Graphing. Okay, I guess we can just first put in our formula since the entry line is just right here waiting for us. Okay, looking back at our question, it is x times y. And be a little careful on this. Alright, here's x. Now I got to put the multiplication sign. I can't just use juxtaposition. The calculator might think there's some variable whose name is xy. So it has to be multiply by and then y. And I don't want to just put a parenthesis next to the y because it'll be trying to maybe evaluate y at some particular argument here. So another multiplication sign to be safe. And now the parentheses, and what follows is 108 minus 2x minus 2y. We'll say enter there. Okay, we start seeing like vertical walls because we don't have nearly the kind of coordinate system needed to fit this. That's not a surprise. And let's start off by getting things under control here. Let's go to the menu and get the range zoom, the range settings. Okay, for x, we need 0 to 36, and so let's use that now. 0 tab, 36. Tab, scaling, maybe 6 apiece, since 6 divides 36 evenly. What the heck? Okay, and the y-axis, same thing. 0 tab 36. Scale it every 6 units, perhaps. Now the z-axis, for right now, remember the 3D graphing seems to be looking nicest when all the axes have the same length. So I'll just set up a z-axis starting at 0. Now, remember, this z-axis represents volume, not the z of our problem. The z of our problem is the length of the package, so we have to kind of keep track of that as we work along here. And for a z max, let's go with 36 to keep the length of this axis the same, and scale every 6 or so, and push enter. Okay, so here we are. Now, what to do? We've got to get this graph to appear. So what we'll do is we'll need to shrink the graph towards the XY plane, and we've done this before in other videos, and we know that if we take the formula for z and divide it by numbers, that can shrink things. So maybe we go to the tab, come up to our formula, and now let's put it in parentheses. Okay, let's take a guess here. What if we divided everything by 100? Start there, see what happens. Okay, we are indeed making a little progress, but it's not enough. Okay, come back, and let's go down here and let's try 1,000. Okay, it's there. It's all there. And as we look at this, you just kind of take a look around at what's going on. Okay, a nice looking graph. And it looks like that 1,000 that we used was maybe a little too much. Let's see. Let's kind of guess at what we can use to get this to fit. Maybe maybe only 400 will make it fit. I kind of like to kind of fill the space at the same time. So let's call back up the formulation and go back here and maybe just 400 maybe. Okay, yeah, I think I like the way this is looking. Now it's almost time to take a picture of this because we do want the overall function here. Now remember, this has just got x going from 0 to 36, y 0 to 36. We're going to need to sketch in this xy plane those domain lines that go in here and project straight up, and then erase some of this graph in here to get our final look of the overall graph. But at least we're well on the way to making progress here. Just a subjective thing here. For this kind of graph, I sort of like to get rid of this box just for this stage. So I think I'm going to hide the box. Okay, let's see what else. I think I can get a little closer, so I can do that with the multiplication sign here. Yeah, a little closer like that. Let me move maybe about there. Then I like the computer view for final pictures. It seems like it has better resolution. So let me go back to the computer view. Okay, and then we'll capture that page right there. Another thing that needs to be captured is what is the the range window, of all these axes. I need to remember that, so I start labeling these axes properly. And I also will need the formula for z, because the z-axis then needs to be multiplied by the factor we used to get this on the graph, which was 400. So I don't just forget all these things, we'll go back and take a couple more picks here. I'll go back to the regular handheld view for a moment, and let's go ahead and get the range zoom, range settings. Okay, take a page capture there, and let me come down and get the z-axis and another capture image there. Okay with that, and then tab. We want the formula that's being used for z right now, so I remember by what factor I need to multiply those tick marks on the z-axis. It needs to be 400. Just to remind myself, take this picture here. Okay, now all the information is in order as far as what's needed to get the big picture graph. Remember, anybody looking at your solution would like to really see the overall view of things, to feel confident that you've got the correct solution and that kind of thing. Now, the next thing we do need to do is try to actually find the maximum value of this graph here. It looks like the maximum value that's sort of in the middle of this surface is going to be in the domain of our final function, and that's kind of nice. Alright, to start working towards this end. Now remember, the x and y axes are just going from like 0 to 36. Alright, it's the z-axis that we had to actually do a divide by 400 just to get this graph to even appear. Now, you want to have the axes all like the same size to really function in this zooming in process I use. So I'm going to first try to get the z-coordinate here to see just where on the z-axis we need to go before we do anything else. So right now it's just focus on what kind of z value is about the maximum here, so I can start getting the z-axis set up to be only about 36 units long and contain its maximum point. That's the challenge for right now. This will be a matter of doing some tracing here. So let's go menu and trace and z-trace. Okay, so this plane, I'm going to kind of move it up and get to the peak point. Okay, right now this plane is moving very quickly. Alright, so I can change that. I'll go back to the menu, tracing. Let's go to trace setup. The default is always 20 steps per z-axis length. For something like this, I tend to go and do the most steps I can to get the most precise control of that tracing plane, and I'll put it at 200. That's the most you can use. Okay, put it at 200. Alright, now back to here and start going upwards with the plane. Okay. Alright, let's look at the top view perhaps and keep moving up. I like to try to just get one little square of, okay, that's too much. Alright, let's say there. Now let me look at that z. Right now it says 28.98. What if I go down one? Okay, it's 28.8, 28.98. Okay, and if I go up one, 29.16. Okay, so it looks like if I had the base of this graph at 28.98 times 400, I would be able to fit things. Okay, you know what? So for just a moment, what is 28.98 times 400? I can go to the scratch pad for a calculation like this. 28.98 times 400. Okay, 11,592. All right. Let's we'll say, so let's say 11,600. Okay, 11,600. That'll be our z minimum. See if this works out for us. Okay, so we go back here to the range trace, range settings, and the new z min will be 11,600. Okay, and now what about the z max? All right, and we want to make this thing like 36 units long, like the other two axes. So I'll just say 11,636 for right now. Find two things after we see the result of doing this. So click OK there. Now, of course, you don't see anything because we need to go back to the entry line and change our z formula to be actual z. No more of this divided by 400. We're trying to say goodbye to that idea. Hitting enter. Okay. Now we seem to see this. The thing I like to have back actually at this point is that box. So bring back the box. Okay, here we are. Now let's look. Okay, you know what? This is actually working pretty well. We got the x and y axis going 0 to 36, and now we're seeing the very peak of that z. We haven't quite got it. Okay, we need to go up higher to get it, it looks like. Alright. Now the axes don't have to be exactly the same length, just kind of close. So right now it looks like we could actually maybe start our graph at this number here, or maybe even a little higher. Let's say 11,640 and go up from there. Okay, menu, graph range, range setting, down to Z. Alright, 11,640, tab down, and now let's make it 36 more than that. So let's see, 646, 76. Okay, here we are. You know what? We have got the maximum value of this function in sight. The z does not go any higher than that. Okay, now that we have each axis the same length and they're all using 1 unit per tick mark, they're 36 units long. Now I can start to really hone in on the peak point of this graph very easily. Okay, let's do another trace. Okay, now I'm going to watch this plane. I'm going to start watching the x and y axis as well. This graph is dead center of the current x and y coordinate plane there. So since they go 0 to 36, it looks very much like close to 18 for x, 18 for y. To get the z, let me make this trace plane go up a bit and see where we have. At one point we leave the graph, so it's up, 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 up. And oh, okay, that was too much. Go down there. Okay, so here come our numbers here. Now let me see how much I'm changing z if I go up and down one from here. Right now it's 11,663.7. If I go up, it's okay, about 664. Okay, so it looks like 11,664 for our z, and the x and y each seem to be about 18. Okay, so here goes the zoom in. Remember, the numbers we think are about right are 18, 18, 11,664, and that's where we center our next axis about. So back here, range trace, range settings. Okay, if we're going to have 18 be in the center of something much smaller than 0 to 36, let's just say 1 unit to the left and 1 unit to the right of 18, so like 17 and 19. Okay, now we'll start scaling that axis as 0.1 per tick mark. Y, same thing, 17, 19. Scaling at about 0.1 per tick mark. Now we said here for the z it was going to be 11,664. Okay, so let's say 1 unit less than that would be 11,663, and then we'll say here 11,665. Okay, this might do it for us. Let's take a look what we have. Okay, yeah, this is looking nice. Alright, now we can really, from here we'll be able to answer our question here. It looks like by just raising this plane a little bit, so it's shift arrow up. Wait a minute, it's moving a lot. Sometimes you need to kind of reset that tracing feature, so let's go here, tracing, trace setup. If you just come here, click, and then go OK, that should slow it down. Okay, now tracing again. Okay, now let's go. Yeah, now it's just moving very small amounts per click. Let's sight straight down. Okay, now if we come up. Whoops, too much. Okay, about there. I'm looking at that Z. It's about really close to 11,664. If I go up a notch, it is 11,664. If I go down a notch, okay, it's barely changing. Okay, so this gives us the conclusive statement that our maximum volume to the nearest cubic inch we now have, that's going to be 11,664 cubic inches, and we have the x dimension to the nearest inch because we can clearly see it is indeed 18. It's not 17, it's not 19, it's 18 inches for x. Similarly, it's 18 inches for y. By the way, I want to have this graph going with my graphic picture I want to draw of this. So now that I have this zoomed in version, maybe about like that, I think I will take a capture of this. Okay, and this is already very clearly labeled, so I don't have to do so much on this one. Keep that and create the final graph. And at this point, the other remaining issue, again, is to go to that scratch pad for a minute. And looking back at our formulation for Z, we had Z equal to 108 minus 2x minus 2y. So right now we need 108 minus 2 times 18, and then minus 2 times 18. Okay, so we think the length of the package should be 36. So we're ready to make a statement about that. We do want to. I want to get the graphic information for the reader in order next. So I'm going to take those images that I've captured, touch them up in Microsoft Paint, and present the final graphic for this problem. Okay, here's the final result of the graphic approximation for this question, and on the left there is the big picture, the graph of V versus all the permissible xy's. The domain is sketched there on the xy plane, and you see there are those couple boundary lines there. The domain is shaded in the light purple, then projects straight up, and I had deleted some of the graphs so that there wasn't that extra graph as would appear in the calculator due to the fact that it wasn't doing the restriction as the domain required. And this isn't exact, of course. It's approximate, a visualization of what to delete and that kind of thing. But anyway, the basic idea of the basic big picture graph is here on the left, and then the zoom in, which is provided with a little circle to show where it comes from, and the zoom in picture there on the right, where we pretty clearly show that we have this peak point at about 11,664, which, remember, that's the x dimension for the package, y dimension for the package, and it's volume V that's being sketched on the vertical axis. And as you see, I've gone back and I actually deleted the way that the calculator had those axes, the vertical axis labeled there, and instead of a Z, which would be incorrect for us, I relabeled it as V. And also in the first big picture graph, I try to put not only the quantity, but its unit to measure as well. For instance, x is in inches, y is in inches, and the volume there is on the vertical axis, and it is in cubic inches. Okay, last thing we need to do is just write up a summary statement. Okay, and so now we have our conclusion written up here. Therefore, a maximum volume of 11,664 cubic inches can be achieved by using a box of length 36 inches, width 18 inches, and height 18 inches as illustrated. Question like this, you want to provide a diagram of your final box and try to make it somewhat to scale so that the proportions that the box has are clear to the person looking at your solution. Okay, the last thing remaining to do here is to kind of check this over a bit to make sure that we are really 100% confident, or at least 99% confident, that there has been no major error in this solution. Okay, so we're on to checking things here a bit, if we can. And one way we might check something like this would be to challenge this design with a couple of just arbitrary boxes we can think of. So let's challenge this optimal claim with a couple other designs. Let's see what happens. Okay, for instance, I don't know, maybe we try like 20 inches. 20 inches. And then what's left over here? This would have to be, let's see, you get with the 108 rather, minus this girth, 20, 40, 60, 80. That'd be 28 inches. Is that permissible? Yeah, it's still the length. Okay. All right, let's try the volume here. V would equal here 20 squared times 28 equals, let's see what happens. We can go to the calculator to resolve this on the scratch pad. Okay, so we got here this 20 squared, and then the times 28. Okay, 11,200. Ah, good. Not better than our optimal design. 11,200 cubic inches, less than the 11,664 cubic inches. That's good to see there. Okay, and as a second challenge, perhaps we could consider a cubic package. Okay, so something about like this. Alright, let's see, what do we got for dimensions if we do this cubic idea? We have x equals y equals z, so when it comes time for saying the z plus 2x plus 2y equals 108, this now becomes x, 2x's, 5x equals 108, and so x equals 108 over 5. Okay, so then the volume of such a package okay, so for checking this number, we can go with 108 divided by 5, the quantity, caret, third power, enter. Okay, what we want is actually a decimal number for comparison purposes, so we can enter here, and now let's go with control equals 2 to get a decimal. Okay, 10,078 approximately, which is also less than the 11,664 cubic inches. Okay, that's a check too. So this optimal design seems to be surviving the challenges of arbitrary checks, so we'll consider this to be a pretty good solution. Okay, for algebra students, all done. Okay, let's try out a calculus solution to this question. Rewritten our math model here on the left side, where we're trying to maximize v equal to xy times parenthetical quantity 108 minus 2x minus 2y. And subject to this system of inequalities described our domain, which we graphed. And I printed a copy of our Nspire graph right here on the right side. The first inequality here, you may recall, ended up being redundant and doesn't affect the graph of the domain anymore, but these others all do. Okay, to find our maximum value here in calculus, what's our responsibility? Well, the basic strategy is to check out critical points, and secondly, examine the boundary, and then do a tabulation of all of the candidate points and see which one leads to the maximum value. Okay, so let's get started here with critical points. Kind of part one of the two-part strategy. Alright, so first of all, we're going to have to take a look at the partial derivative of v with respect to x. Right now, this maybe could be written as just a expanded polynomial, which is a little more suitable for differentiation, I suppose. So we multiply this out here. This would be 108 xy minus 2x squared y, and then minus 2xy squared. Okay, now starting here, dv dx, partial derivative, and what do we get here? Looks like we're going to get a 108y minus a 4xy, and then minusing 2y squared. Alright, and the concern for a critical point, first of all, is the dv dx equaling 0. That'll occur if and only if 108y minus 4xy minus 2y squared is equal to 0. Okay, so we start working on this equation here. Well, it looks like a factorization is immediately available. Take advantage of that, of course. 2y factors out, leaving behind 54 minus 2x, and then minus a y. Okay, great. Having a factorization equal to 0 allows us to split this up into 2y equaling 0, or our other factor here equal to 0. Okay, let's work here for a minute. This, of course, just becomes y equal to 0. Now, if we think what this is about, y equal to 0, well, this is not in the domain of our function at all. The y equal to 0, the x-axis, in other words, it's not in our domain. Remember, we have y greater than 0 as one of our inequalities there, so this is not in the domain of v, so it's gone from consideration. Moving over here, alright, let's see, we seem to have a straight line going on here. Maybe we write it in standard form just before we walk away from it for a while here, so we could have 2x plus y equals 54, and leave it at that for the moment. Okay, well, to be a critical point, you have to satisfy both partial of v with respect to x equals to 0 and partial of v with respect to y equaling 0. So first let's get this partial derivative calculated, back up to the original formulation, and let's see here, we would have a 108x minus a 2x squared, a minus a 4xy. Then, to consider dv dy equals 0, that occurs if and only if 108x minus 2x squared minus 4xy equals 0. Here, factorization is available at first. A 2x factors out, leaves behind 54 minus x minus a 2 and a y. Okay, so now this breaks up into a pair of equalities, or 2x equals 0, or 54 minus x minus 2y equals 0. Okay, let's work on this. This divide both sides by 2. X equals 0. Alright, x equals 0. This is then referring to the y-axis itself. You know what? This is not in the domain of our function v here. So that's not in the domain of v. Cancel considering that any further. This, alright, some sort of straight line. Put it into standard form, I suppose. X plus 2y equaling 54, in other words. And there's our result of dv dy equal to 0. Boiled down to just this line of xy's here. Now, to get the critical point, of course, you got to solve the system. dv dx equals 0 and dv dy equal to 0. So let's go on to that. Alright, so we need to solve a system. dv dx equals 0. 2x plus y equals 54. And our partial of v with respect to y equal to 0. We found that only occurs when we have x plus 2y equaling 54. Okay, as far as the system goes, it's a linear system. 2 equations. Okay, not bad. We can solve with a pretty easy elimination method. Let's say first equation minus 2 to the second. Alright, 2x minus 2x's. They're eliminated. Y minus 2 by 2y, negative 3y. 54 minus 2 times 54, negative 54. Okay, so it looks like y is positive 54 over 3. And what's that? 18. Okay, to get the corresponding x, we can go to recycle this second equation. Looks easiest. We'd have 54 minus 2 by the 18. 54 minus 36, we're at 18. Okay, so now we're sitting here with this point 1818. We got to wonder about, is this in the domain of the function? Looking back at our graph, 1818 clearly is in the domain of function v. So it looks like we've got ourselves the claim that 18 is a critical point. And it's the only one, too. Okay, now, actually interesting question I could ask here, and that's that, okay, so we have this one critical point. We could analyze this using some second partial derivatives and determine whether or not there is a relative min or relative max at 1818. Alright, we're trying to find our maximum value of v here. Suppose we do this, which wouldn't take too much effort, and find that there is a relative maximum of v at 1818. Could we then say that, since that's the only critical point in the function, could we say then there's no chance of it ever achieving a higher value thereafter and avoid even dealing with the boundary consideration? You know, in a real valued function, the answer is that's correct. If you find a real valued function has a relative maximum at a point, and it's the only critical point, and the function cannot possibly then turn around and achieve higher values, it would expose itself by means of another critical point. Okay, functions of two variables are not like that. Despite this function having a relative maximum at 1818, it could very well, that surface could very well turn around and have higher values of volume without ever leaving behind another critical point in its wake. So you've got to be careful here. We really do have to, mathematically speaking, examine the boundary here. Okay, so let's go to that next. Okay, to start this boundary examination, I've put a new page up here with the problem rewritten, and so it's in sight for us. And as far as getting ready to examine the boundary goes, we might first maybe clarify this graph a little bit as far as what the boundary actually looks like, because with the x and y axis here, one feature didn't really get clarified, I don't suppose, and that's that the x-axis and the y-axis are not part of the domain of this function. They are only boundary lines. Okay, so maybe a little bit of clarification going on here. And for instance, this point 360 is supposed to be a hollow circle there. Of course, the origin is a hollow circle, and this point here would be a hollow circle as well. This point here, by contrast, this is the intersection of two solid lines, inequality borderlines, so this would actually be a solid line there. Then, as far as these boundary lines go, from the L3 in the blue, that's here, the 1x minus 2x, that was an or equals to inequality, a solid boundary there. This one here, also a solid boundary line. Okay, that came from this other inequality here, which was an or equals to variety. Now, these boundary lines here are, strictly speaking, dashed lines, because it was x greater than 0, y greater than 0 that defined these. So I just kind of want to clarify this issue, since right now boundaries are the center of attention right now. Okay, and another thing to keep in mind, now realizing that mathematically speaking, function v here is not continuous on a closed and bounded interval. It's actually a continuous function. However, the domain here is not closed with these dashed lines here and here. So we're actually not assured mathematically that this function even has a maximum value nor a minimum value. But okay, we proceed. Something else comes up getting ready to study this boundary problem, and that is something we could take advantage of, because after all, boundary work is kind of time consuming and tedious. So if something comes along as a shortcut, take advantage of it. And here, if you notice the formulation of the function v here, you actually could interchange x and y and have the same formulation pan out. That means that the function v is symmetric with respect to the diagonal line y equal to x. The domain of this function also happens to have that symmetry as well. Draw the y equal x line. If it was squared off, you'd have a couple of congruent regions there. You could fold one over the other, and you have the symmetry with respect to the diagonal line y equal to x. So if we notice that symmetry, this means we need only study 1/2 of the function, in a sense, to one side or the other of the y equal x line, and we can just use symmetry to reflect any results across to the other side of the line. So our first statement here could be note the symmetry of function v with respect to the diagonal line y equals x. Okay, having said that, although this boundary consists of 4 line segments, L1, L2, L3, L4, it is sufficient to examine boundary lines L1 and L2. So, it is sufficient to examine only L1 and L2. Okay, let's start there. Alright, so let's begin with line segment L1. I like to call these line segments, so I'm going to name them L1, L2, L3, L4 with little bars on the top so they don't appear to be full-fledged lines. And for L1, what about that? Well, the equation there is the y equal to 0. And another thing to note is that the function v, rather L1, is not actually part of the domain of this function. So now what do we do? Okay, we could at least consider the limit as xy approaches our L1 of v. And what goes on there? Alright, since L1 has the equation y equal to 0, As you get close to L1, you have your y becoming near 0. Going back, looking at the formulation of v here, y getting very near to 0 since it appears as this factor here, and at the same time x is at least bounded. It's sitting here between 0 and 36. So we're sitting here with something that pretty essentially, due to this y here, zeroes out in the limiting sense. So get a 0 for that limit as far as the value of v as the points get very near to L1. Okay, let's move on to line segment L2. In this case, let's see, now this was a part of this green line. The equation there was the y equals to 108 minus 3x over 2. Okay, now let's see, what we need to do to examine function v along this line is we now need to actually come up with algebraically what is v of x and replace the y with this expression, 108 minus 3x over 2. Okay, well, this is a rather tedious algebraic computation, and we have our Nspire available to us, so let's maybe go ahead and take advantage of the computer algebra system to crunch this out for us right now. Let's go there. Okay, so let's open up a new page, Control, new page, and let's use some calculator application here. So the idea is to come up and figure out, okay, no, wait, let's check something here. Right now, what have we got in Z1? Since we did some transformations, we should make sure we have the actual volume function here, not some factored version of it. Okay, no, we have the original actual function v sitting in Z1 right now. Good. Okay, this means we can now go ahead and proceed with Z1 of x and replacing the y with a 108 minus 3x divided by 2. Okay, get that. Alright, so let's make a note of that on our paper here. Okay, so now we have the result of what is v when we substitute the 103 minus 3x over 2 for y. Get this here. Now what we're interested in is the dv dx equal to 0 in this case, the critical points here. Now, since it's polynomial, there's no undefined cases, but again, we're trying to get the dv dx equals 0. Heck, another chance to use the Nspire. Why not? Okay, what can we do here? Well, let's see. Let's create a function. We'll call it z1 along L2. So I'll call that z1 L2. And we will assign that to be equal to. And I'll kind of go back up here for a minute and enter that. And now we have that. Okay, so with this in mind, let's go ahead and now solve a derivative equal to 0. Okay, so let's go to the menu and go to the algebra, solve, and now let's take a look at a derivative. Okay, with respect to x of our z1 L2, and we're solving that equal to 0. The variable is x. Go. Okay, so now we come up with this x equal to 0 or x equal to 24. Okay, let's see what we think about that. Now, we're on this L2. X equal to 0. Well, wait a minute. That's actually not a corresponding to a point on L2. So this is not an element of L2. cancel that consideration. 24. Looking here at this L2. Now L2 begins with an X starting at 21.6 and up to 36 for the X. Okay, this is going to be on L2. Let's find the corresponding Y. The Y would equal to, using the L2 equation, we're looking at 108 minus 3 times 24 over 2. That would be, let's see, 3 times 24, we're up to 72. 108 minus 72, 36 over 218. Okay, so it looks like we got here 24, 18. This is a candidate. Alright, so we have this candidate 24, 18. We have symmetry also. By symmetry, we get reverse the interchange the coordinates there. 1824 is a candidate. It's a candidate point at which the volume may turn out to be absolute maximum. Okay, is there anything else to concern ourselves with? Okay, thinking about this L2, we also need to consider the boundary points for L2 itself. Okay, now this one here, this 36,0. So, boundary of L2, the line segment. Okay, the 36,0 has already been addressed because it was on L1. It was addressed there. So addressed during the L1 examination. That's done. The other side has got this point 21.6, 21.6. It's on L2, and well, that's a candidate. Okay, candidate there, candidate there, candidate there. Okay, so from our boundary consideration, we've generated 1, 2, 3 candidates. Our critical points, there was one of those, and so now we're ready to do our tabulation. This aspect is probably best done on the Nspire, so let's go back there. Okay, let's see, for this tabulation, this is probably something that's best done on a spreadsheet. So we could go ahead and Control, add a page, and let's go with a spreadsheet. Let's see, in this column we'll put the X coordinates of the candidates, so maybe I'll label those as X candidate. X can for short. And here we'll put the Y coordinate of all our candidates, candidate points. Y candidate, and here will be the volume calculation. All right, so we can go with volume there, perhaps. Okay, let's start putting our points in here. So we looking back at our critical point calculation, and we had 18 and 18 there. Alright, now at our first boundary point consideration, we had 2418. And then we also had the 1824. And we also had the 21.6, 21.6. Okay, now what we need is to know what the volume is at each of these. So here in the formulation line, we might go ahead and let this be equal to Well, right now our volume formula is already in here. It's tied up in Z1. So we can say Z1 of, and for right now we can just use the simplest reference of all to the X candidates here, which is just the letter A as far as the spreadsheet goes, and the Y candidates are most simply referred to, I suppose, by just simply a letter B here. So I'll go with an A and B for the arguments of that there, and we enter. Okay, what have we got here? Looking for the largest volume. There it is. It's actually sitting there in line 1. Okay, 11,664. That'll be cubic inches. And you know what? This is really good to see. The reason being, this is consistent with what we had discovered on our graphic approximation to this problem done in the first part. Okay, so the only thing that remains is to calculate the last thing, being the z dimension of this package, and then we seem to have everything being tied together. So going back to that formulation, at 1818, it'll be the same as what we computed in our graphic formulation. That leads to a z of 36 inches. Okay, we're ready to write a conclusion. Okay, so I've taken that table that we just created on the Nspire and printed it up right here. And again, this is the tabulation of values at candidate points, and we've coming in right in here and interpreting what this line means with our maximum volume. We have got the conclusive statement that a maximum volume of 11,664 cubic inches can be achieved by a box having the dimensions illustrated. And this time we will just draw a simple hand version of what we did very nicely in the first part, and that is the 18 inches here, 18 inches here, and the length 36 inches there. Okay, and finally our check on our work here, and that is that this calculus solution is consistent with the graphic approximation performed earlier. So this calculus solution is consistent, that's the exact same conclusion as the graphic approximation performed previously. Looks good. Prominent box on the conclusive statement here, and there we are.